Good evening. Welcome to Deep Sleep Manufacturing. Tonight, we embark on one of the most ambitious and complex engineering projects that humans undertake: the construction of an underground metro transit system. This is not a simple project. It requires meticulous planning, advanced engineering, tremendous coordination, and an almost meditative attention to detail across years of construction. Our journey takes us to a major metropolitan area where a new metro line is being constructed. The project spans 25 kilometers underground, connecting 11 stations throughout the city. The work has been ongoing for nearly 4 years, and we're now at a critical phase where tunneling is complete and the installation of tracks, electrical systems, and station finishes is in full progress. The metro system represents a fundamental change in how a city moves. It will eventually carry hundreds of thousands of people daily, reducing traffic congestion, lowering emissions, and providing rapid transit. But before a single passenger board, countless systems must be installed, tested, and verified. The project began years ago with planning, environmental assessment, and geological surveys. Engineers studied the soil and rock beneath the city to understand what they would encounter during excavation. They mapped the locations of existing utilities, water pipes, electrical cables, communication lines that must be avoided during construction. The planning phase established the route. 37% of the route passes through clay and silt. 28% passes through sandy layers. The remaining 35% passes through solid bedrock. Each geological layer requires different excavation techniques. This variation necessitates careful planning and adaptive strategies. The station locations were selected based on demographics, land use, and integration with existing transit systems. Each station will serve a specific purpose, some serving commuter rail connections, others serving bus terminals, still others serving shopping and entertainment districts. The environmental impact was assessed exhaustively. Water table changes, ground settlement, noise from construction and operation, all were studied. Mitigation measures were designed to minimize negative impacts on the surrounding community. Safety planning was extensive. With tunnels extending 40 to 60 meters below the surface, safety protocols are critical. Every worker on the project receives extensive safety training. Safety equipment is mandatory. Regular inspections ensure compliance. Now we're in the active construction phase. Tunneling is complete. The boring machines, enormous mechanical devices that created the tunnels, have been retired. They've been disassembled and removed from the site. The tunnels they created are now being transformed into a functioning transit system. Let us journey back to understand how these tunnels were created. Several years ago, when the project was in its early phases, massive tunnel boring machines, commonly called TBMs, arrived at construction sites. A tunnel boring machine is one of the most impressive pieces of engineering equipment ever created. The machine we're discussing is approximately 10 meters in diameter and 120 meters long. At its front is a rotating cutting wheel, a circular face studded with carbide cutters, capable of grinding through rock, clay, and everything in between. The cutting wheel rotates constantly as the machine advances. The rotational speed is carefully controlled, perhaps 2 to 4 rotations per minute. This slow, methodical speed prevents overloading the cutting tools and ensures clean, stable excavation. As the cutting wheel rotates, its carbide cutters bite into the rock and soil ahead of the machine. The material is pulverized and fragmented. The broken rock falls into a collecting chamber, the center of the cutting wheel. Inside the TBM, a sophisticated system manages the excavated material. A conveyor belt carries the broken rock from the collection chamber toward the rear of the machine. The material is transported approximately 100 meters through the machine to the rear discharge area. Here, the rock is loaded onto another conveyor system that transports it back to the surface. The surface conveyor system is equally impressive. A conveyor belt extends from the tunnel portal, the entrance point where the TBM operates, all the way to the surface. The excavated rock is continuously carried to the surface, where it's deposited in massive piles. This excavated rock will eventually be used for landscape restoration or sold to construction aggregate suppliers. The volume of material being excavated is staggering. The TBM is advancing approximately 15 meters per day. Each meter of tunnel advance requires the removal of approximately 70 cubic meters of rock and soil. Multiplied across the 25-kilometer length of the project, this represents nearly 2 million cubic meters of excavated material. Managing the excavation face, the front of the tunnel being actively cut, is critical. The pressure at the excavation face must be carefully controlled. If the pressure is too low, the tunnel walls could collapse. If the pressure is too high, the ground above could heave and settle unexpectedly. The TBM has sophisticated systems to measure and maintain the exact pressure required for stable excavation. As the TBM advances, it simultaneously installs tunnel support structures. Behind the cutting wheel, large concrete rings, called segmental linings, are installed. These rings, each approximately 1.5 meters in height, form a complete circle around the tunnel. The rings are precision manufactured to exacting tolerances. They must fit together perfectly, creating a continuous support structure. The installation of these rings happens automatically within the machine. Robotic arms position each ring segment. Hydraulic presses push the rings tight against the tunnel walls. The arrangement is precise. Each ring sits perfectly against its neighbors, creating an incredibly strong structure that will support the tunnel permanently. The TBM advances methodically. 10 meters per day might not sound fast, but the work is continuous, 24 hours per day. The machine operates without stopping, 3 shifts per day, 7 days per week. The advance is measured, controlled, and carefully monitored. Dozens of workers operate the TBM. The machine operator, sitting in a control room inside the TBM, monitors the advance, making constant micro-adjustments to maintain perfect alignment. Laser theodolites mounted on the TBM verify that the tunnel is being driven in the exact planned location and at the precise grade, slope, required. Geotechnical engineers monitor the stability of the tunnel. They examine the rock being excavated, looking for unexpected conditions, water flows, unstable clay layers, or other surprises. The engineers adjust the machine's operation to adapt to changing conditions. As the TBM advances, additional work progresses behind the machine. Ventilation ducts are installed. Electrical conduits are routed through the tunnel. Water pumping equipment is positioned. Temporary lighting is installed to illuminate the tunnel as construction progresses. The TBM operator describes the operation in simple terms. The machine is advancing through clay and sandy layers. Rock pressure normal. Segment installation proceeding perfectly. Advance today, 14.6 meters. Total advance to date, 12,347 meters. The tunneling process is methodical and hypnotic. The cutting wheel rotates continuously. The conveyor carries material steadily. The segmental rings are installed in a rhythm. The machine advances inexorably toward its destination. For the boring machine operator, the work is watching, monitoring, and adjusting. It's not frantic activity. It's careful observation and patience. The machine is powerful, but it's operated with surprising gentleness and precision. The TBM is driven not by aggressive action but by meticulous monitoring and patient progress. After approximately 4 years of continuous operation, the various TBMs used on the project reached their destination points. They've excavated approximately 100 kilometers of tunnel across the network of metro lines. The machines are then disassembled and removed from the tunnel. The tunnel boring equipment is a temporary tool. Once its purpose is served, it's extracted and repurposed for future projects in other cities. With the tunneling complete, the tunnels require finishing work to create the structure that will support the track, electrical systems, and all other metro infrastructure. The first major step is installing the permanent bottom concrete layer, called the invert concrete. Crews enter the completed tunnel with machinery and materials. The tunnel is dark except for temporary lighting strung along the length. The temporary lights create pools of illumination in the darkness, revealing the segmental ring structure of the tunnel walls. The invert, the bottom surface of the tunnel, is being prepared for concrete. The segmental rings create the circular tunnel shape, but they create an uneven surface where segments meet. This needs to be smoothed and leveled before concrete is poured. Workers spray a waterproofing membrane onto the tunnel bottom. The spray creates a protective coating that prevents water seepage into the concrete. The spraying process produces a soft hissing sound as the membrane is applied. The workers move methodically along the tunnel, ensuring complete coverage. Concrete forming is set up on the tunnel bottom. Wooden forms or metal rails create a smooth surface onto which concrete will be poured. The forms are positioned precisely. They must be perfectly level so the resulting concrete surface is uniform. Reinforcement steel is positioned in the forming. Steel rebar creates a grid that will strengthen the concrete and prevent cracking. The rebar is tied together with steel wire in a systematic pattern. Workers move carefully through the temporary forms, ensuring every connection is secure. The concrete arrives in mixer trucks. The trucks back into position at the tunnel entrance. Their pumping equipment extends into the tunnel. The concrete is pumped through large diameter hoses toward the forming area. The concrete flow is controlled, not rushed but steady and continuous. The concrete fills the forming in layers. As each layer accumulates, it's vibrated using mechanical vibrators. The vibration helps the concrete settle and removes air pockets, ensuring the concrete achieves maximum density. The process is slow. A section 100 meters long might take 8 hours to pour. The concrete must be vibrated thoroughly. The surface must be smoothed and leveled. No rush. No shortcuts. The invert concrete is structural. It will support track loads for the next 100 years. As the concrete hardens and cures, the next section is prepared and poured. The work progresses along the tunnel in segments. Each segment is completed, cured, and then the next begins. The progress is steady but unhurried. Workers stand at the concrete surface with straight edges, checking that the concrete is perfectly level. Laser levels are used to verify elevation. Any high spots are smoothed. Any low spots are filled. The precision is critical. The track system that will eventually be installed requires a perfectly level surface. The curing process takes 2 to 3 weeks. The concrete is kept moist with periodic water spraying. This ensures the concrete hydrates properly and develops full strength. The spraying creates a refreshing mist in the tunnel, a small break in the otherwise dry environment. By the completion of this phase, the entire tunnel has a smooth, level concrete bottom. The tunnel has transformed from a bare rock structure to a prepared foundation for the next systems. A metro system must have sophisticated ventilation. Trains generate heat as they operate. Passengers generate body heat. The station and tunnel environment must be kept comfortable and safe. The ventilation system includes large ducts installed above the track area in the tunnel. These ducts, approximately 2 meters in diameter, carry air along the tunnel length. Fans at specific locations push air through the system. The airflow is designed to remove heat, odors, and maintain proper air quality. Workers install ventilation duct sections. The ducts are large cylindrical structures made of sheet metal. They're positioned on supports above the track area. The installation requires careful coordination. The ducts must be positioned without interfering with track space or other systems. Each duct section is approximately 2 meters in length. Workers position the sections and weld them together, creating a continuous duct that extends the full tunnel length. The welding process produces bright sparks in the dim tunnel lighting. The sound is a continuous hissing as the welding torch creates the joints. The ductwork is sealed. All seams are welded or sealed with special mastic. No leaks are acceptable. Any air leakage would reduce system efficiency. Workers carefully inspect each joint, ensuring complete integrity. Supply air openings are cut into the duct at strategic locations. These openings are fitted with dampers, control devices that regulate airflow. The dampers can be adjusted to control how much air flows into the tunnel at each location. Return air ducts are installed at the ceiling level, above the supply ducts. These collect warm air from the tunnel and return it to ventilation plants above ground. The two-duct system, supply and return, creates continuous air circulation. At station locations, the ventilation system includes additional features. Supply air plenums, large chambers, distribute air evenly throughout the station. Return air shafts collect air from the station environment. The stations require greater ventilation capacity than the tunnel sections, as the volume of air that needs to be moved is greater. Ventilation equipment installation is complex. Large fans, some driven by electric motors with horsepower ratings exceeding 1,000, are installed in separate ventilation plants above ground. These fans create the pressure differences that drive air through the system. The installation of ventilation equipment happens simultaneously with ductwork installation. By the time ductwork is complete, the fans are being tested and balanced. Airflow rates are measured. The system is adjusted so each location receives the correct amount of air. Testing the ventilation system is detailed and methodical. Anemometers, devices that measure air velocity, are positioned throughout the tunnel. Measurements are taken at multiple locations. The data is analyzed to ensure the system is performing correctly. Supply air velocity at position 1, 2.3 meters per second. Target is 2 to 3. Acceptable, an engineer reports. Return air velocity at station 1, 1.8 meters per second. Target is 1.5 to 2. Acceptable. The balance continues until the entire system is verified to perform within design parameters. The system is then shut down. It won't be operated until the metro opens for service. For now, it's simply tested and ready. The metro system requires sophisticated electrical systems. Track power systems provide electricity to the trains. Lighting systems illuminate tunnels and stations. Control systems monitor and manage operations. Communication systems enable dispatch and emergency response. The track power system is installed first. 2 parallel rails run along the tunnel length. These are the running rails that the train wheels contact. A third rail, positioned at a safe height to the side, carries electrical power. The third rail is called the live rail or hot rail. The installation of the live rail is done with extreme care. This rail carries thousands of volts of electrical power. Safety is paramount. Insulators are positioned at regular intervals to prevent electrical current from leaking into the tunnel structure. The live rail is fed power from substations located above ground. Massive electrical cables run from these substations down into the tunnel, connecting to the live rail at specific feed points. The electrical cables are larger in diameter than a person's arm and contain hundreds of copper conductors. The cable installation is a major undertaking. At each substation, electrical equipment converts the city's power supply to the specific voltage and current required by the metro system. Transformers step voltage up or down. Rectifiers convert alternating current to direct current if required. Switching equipment controls which portions of the track are energized at any time. Lighting installation proceeds in parallel. Thousands of LED light fixtures are installed along the tunnel and in all stations. The fixtures are positioned at regular intervals, approximately every 20 meters in the tunnel, more densely in stations. The lighting design is sophisticated. The fixtures provide sufficient illumination for safe operation and maintenance, but they're not excessively bright. The design considers the human eye's response to different light colors and intensities. The chosen color temperature, a cool white light, is shown to reduce fatigue during extended periods in underground environments. All lighting is controlled by automated systems. Sensors detect when areas are occupied. Lights increase to full brightness when people are present and dim to lower levels when areas are unoccupied. This reduces energy consumption while maintaining safety. Communication cables are installed in conduits running along the tunnel. These cables carry voice communications, video from monitoring cameras, and data from various sensors. The cables are separated into different conduits to prevent interference between systems. Fire detection systems are installed throughout. Heat detectors and smoke detectors are positioned at regular intervals. The detectors connect to a central control system that alerts staff if smoke or excessive heat is detected in any location. Emergency lighting, battery-powered fixtures that activate if main power fails, is installed along escape routes. These lights ensure that even if the main electrical system fails, people can safely exit the tunnel and station. Electrical testing is extensive. Every circuit is tested for proper voltage and current. Every light is tested for proper operation. Every detector is tested to ensure it responds correctly to actual conditions. The testing takes weeks and involves dozens of electricians. With the structural systems in place, ventilation and electrical, the track system is now installed. This is where the metro's most visible component takes shape. The track consists of two parallel rails. Each rail is made of hardened steel, forming a typical T-shaped cross-section. The rails are continuously welded to create seamless lengths that can extend hundreds of meters without joints. The rail installation is precise. The rails must be positioned with extreme accuracy. Track gauge, the distance between the two rails, must be maintained at exactly 1,435 millimeters. Any deviation would cause problems for the trains. Rail positioning is done using a track-laying machine, a sophisticated device that positions and secures rails in their final location. The machine uses laser theodolites and digital measurement systems to position rails with millimeter-level precision. Sleepers, also called ties in some regions, are placed beneath the rails at regular intervals. The sleepers are concrete structures that sit on the tunnel invert, the concrete bottom. The rails are fastened to the sleepers using specialized fastening systems that allow small adjustments while maintaining security. The fastening systems must accommodate thermal expansion. As temperature changes, the rails expand and contract. The fastening system allows the rails to move slightly without losing security. This prevents unnecessary stress on the rails during temperature changes. Thermal expansion joints are installed at regular intervals. These allow the track to expand or contract without transferring stress to the structure. The joints are designed to allow up to 50 millimeters of movement in each direction. The track must be level and properly aligned. Laser theodolites mounted on tripods measure the track geometry. A sensor on the track-laying machine compares the actual position to the required position. The machine makes continuous adjustments to maintain perfect alignment. The crew works methodically. Install sleepers. Position rail. Fasten rail. Measure geometry. Move forward to the next location. The work is repetitive and meticulous. The sound of the track installation is the ring of fasteners being tightened, the grinding of the track-laying machine's positioning mechanisms, the beeping of measurement systems providing feedback. These sounds blend into the general ambience of construction progress. As the track progresses, workers install points and switches, the devices that allow trains to move from one track to another. A single point installation requires precise positioning of multiple rail segments. The switch mechanism must operate smoothly under load while maintaining absolute safety. Point installation is complex work. The position rails must be aligned perfectly with the running rails. The switch mechanism must be tested repeatedly to ensure smooth operation. Hydraulic systems that operate the switches are tested with no load and then with gradually increasing load. The progress is steady but not rushed. Each meter of track that's installed must be verified to be correct before the next section begins. The overall track length extends over 100 kilometers across all the lines. The detailed work proceeds methodically. By completion of this phase, the track is installed throughout the tunnel system and all stations. The tracks gleam in the LED lighting, ready to support trains that will eventually carry passengers at speeds exceeding 100 kilometers per hour. While tunnel work continues, an equally intensive effort is underway at the 11 stations. Each station is a complex structure that requires substantial work. Station construction began earlier than tunnel finishing work. In fact, some of the larger stations required construction using an cut and cover method. The roof was installed above ground, then excavation proceeded below the roof. This method is faster than excavating first and installing a roof later. Other stations were constructed using the full excavation method. The station box was excavated entirely, then the roof was installed. These stations required careful temporary support during excavation to prevent collapse. The station construction has progressed through concrete structural work, waterproofing, and installation of temporary systems. Now, as we observe the project, the focus is on final finishing and installation of permanent systems. Station platforms are the primary architectural feature. These are where passengers stand while waiting for trains. Each platform must be at the precise height to align with the train doors. The platform height is established as a permanent structural element. Concrete platforms poured during the station excavation phase. The platforms are now being finished with various surface materials. Some stations feature tile surfaces. Others feature concrete with special anti-slip coatings. The choice of surface material is both aesthetic and functional. The surface must provide good traction while being visually attractive. Platform tactile paving is being installed at the station edges. This is a specialized surface with a raised pattern that provides feedback to visually impaired passengers, warning them of the platform edge and dangerous proximity to the track. Station walls are receiving final finishes. Some walls feature architectural cladding, materials that provide visual interest and improve the acoustic environment. Others feature simplified finishes that prioritize cleanliness and maintenance. Lighting installation in stations is more extensive than in tunnels. Stations require sufficient illumination for passengers to navigate safely and comfortably. The lighting design uses multiple fixtures to avoid harsh shadows and create an inviting atmosphere. The stations are receiving mechanical and electrical systems. Elevator shafts connect platform level to street level. Escalator installations are underway. Emergency stairs provide backup routes to the surface. Each of these systems must meet stringent safety and performance requirements. Elevator installation is meticulous work. An elevator is a complex machine with numerous safety features. The elevator is installed in sections. The rails are positioned in the shaft, the car is installed, the machinery is assembled, the control system is programmed. Each step is verified before moving to the next. Escalator installation is equally detailed. The escalator structure is positioned in the shaft. The steps are installed. The handrails are secured. The motor and control systems are installed. Testing begins with no load, progresses to light load, then to full load with multiple people. Passenger information systems are being installed. Destination displays, currently dark, will show train arrival information. Emergency communication systems allow passengers to communicate with station staff if needed. Public address systems will announce arrivals and important information. Fare collection systems are being installed at station entrances. Automated gates, controlled by electronic systems, will allow authorized passengers to enter the station. The gates incorporate both physical security and electronic control. Security systems are extensive. Closed-circuit cameras monitor all station areas. Emergency alarm systems allow rapid response to problems. Lighting extends to every corner of the station, eliminating dark areas. The work in stations is intensive. Multiple crews work simultaneously in different areas. Electricians are installing lighting. Plumbers are connecting water systems for restrooms. HVAC technicians are balancing airflow. The coordination is complex but well managed. As we observe the stations during this construction phase, the activity is intense. The pace is faster than tunnel work. There are more workers, more varied activities, more immediate deadlines. But the fundamental approach is the same. Careful attention to detail, verification at each step, and quality control throughout. Station construction will take several more weeks to complete. The work will continue with the same methodical approach. Install, test, verify, move to the next task. By the time the metro opens, the stations will be complete and fully functional. The metro system requires sophisticated automatic signaling and control systems. These systems manage train movement, prevent collisions, and ensure the safe and efficient operation of the entire network. The signaling system is being installed along the entire track length. Signal equipment mounted on poles or attached to tunnel walls monitors train position. Detection systems, typically electronic loops buried under the track, sense when a train passes over them. The control room for the signaling system is a sophisticated facility above ground. Here, a central computer monitors the position of every train on the network at all times. Train positions are displayed on large screens showing the track layout and the location of each train. The signaling system operates according to strict protocols. The track is divided into blocks, sections typically 1 to 2 kilometers long. The system prevents more than one train from occupying the same block. If a train is in a block, no other train is allowed to enter that block until the first train has vacated it. Signals, light-based devices providing instructions to train operators, are positioned at regular intervals. The signals can display different colors: green, proceed at full speed; yellow, caution, reduce speed; red, stop. These signals guide trains through the network safely. Automatic train protection systems, called ADP in industry terminology, go beyond simple signals. If a train approaches a signal that indicates it should slow down or stop, the ADP system automatically applies the train brakes if the operator hasn't responded. This provides a safety layer that prevents accidents caused by human error. The installation of signaling equipment is detailed work. Each signal must be positioned precisely. Sight lines from the signal must be clear so train operators can see the signal from a safe distance. The power supply for each signal must be verified. The communication connections back to the central control system must be tested. A technician is positioned at a signal location, checking the signal's operation. Signal H21 positioned correctly. Sight line clear for 200 meters. Power supply normal. Control connection normal. Signal response to command normal. Signal H21 approved. This verification process is repeated for hundreds of signals throughout the network. The process is methodical, quiet, and thorough. The central control system software is being developed simultaneously with hardware installation. The software must manage hundreds of trains moving throughout the network without collisions. The algorithms determining train spacing, acceleration, deceleration, and routing are sophisticated and have been developed through years of research and testing. Testing of the signaling system begins with simple scenarios. A single train operates under signaling control, responding to signals as directed. The train is operated at low speed in a confined section of track. Every signal is verified to control the train correctly. As testing progresses, scenarios become more complex. 2 trains operate simultaneously, each required to respond to signaling that maintains safe separation. 3 trains. 4 trains. The system is tested with increasing complexity until the full network of trains and signals is verified to work correctly. The testing involves extensive communication between the signaling team and the train operating teams. Train control. This is signal test. Test sequence 7 beginning. Please move train 3 to block B10. Acknowledged. Train 3 moving to block B10. Train 3 is at block B10. Signal H19 displaying yellow. Train 3 responding with speed reduction. Speed now 60 km per hour. Deceleration rate normal. The communication is calm, methodical, and precise. Nothing is rushed. Every aspect is verified. The control system development includes contingency planning. What happens if a signal fails? The system should safely bring trains to a stop. What if a sensor fails? The system should operate using other information. What if communication is interrupted? The system should operate in a degraded mode that maintains safety. Months of testing precede actual operation. By the time the metro opens, the signaling system will have been tested thousands of times. System reliability is verified to meet the highest standards. As the physical infrastructure nears completion, the trains are delivered to the site. The trains are manufactured at a facility in another city, then transported to the metro system for testing and preparation. The first train arrives on a special heavy-haul transporter, a low-bed truck designed to carry large, heavy loads. The train is driven carefully to the metro entrance. Multiple spotters guide the driver as the train is positioned precisely at the access point. The train is unloaded using a specialized procedure. Hydraulic equipment on the transporter lowers the train gently. Track workers position themselves alongside the train to monitor the positioning. The wheels of the train gradually contact the newly installed track. The moment when the train's wheels first contact the track is significant. The train is being positioned on infrastructure that will support millions of journeys in the future. The precision of the track installation is verified in this moment. If the track is properly aligned, the train will rest securely on the rails. The train is positioned perfectly. The track geometry has been verified accurately. The train settles onto the track, its weight supported by the carefully constructed infrastructure below. The train remains stationary while initial inspections are performed. Maintenance technicians examine the wheels, checking for any damage from transportation. They examine the coupling mechanisms that allow multiple train cars to operate as a unit. They verify that all doors, windows, and emergency equipment are functioning. The train's internal systems are tested. The electrical connections to the live rail are verified. Power is applied. The train's systems activate. Lights illuminate the interior. Climate control systems begin operating. Communication systems come alive. The control system operators verify that the train is appearing on their monitoring displays. The train's location, speed, and status are visible in the control room. Train 1 is positioned at Station Alpha. All systems nominal. Train 1 is ready for movement testing. Movement testing begins. The train operator, sitting in the control cab at the front of the train, follows instructions from the training supervisor. Train 1, move forward at 5 kilometers per hour. Acknowledge. Train 1 moving forward. Speed 5 kilometers per hour, the operator responds. The train begins to move. It's the first time the newly installed track is being used to carry a train. The sound is a low hum from the electrical propulsion system. The track appears to support the train correctly. The operator gradually increases speed. 10 kilometers per hour. 20. 30. The train moves smoothly along the track. The recently installed electrical, ventilation, and signaling systems are all functioning as designed. As speed increases, subtle vibrations are noted. The suspension system, the springs and dampers that isolate the passenger compartment from track irregularities, is functioning, softening these vibrations. The train accelerates to 50 kilometers per hour. The track is smooth. The train is stable. The alignment is correct. The operator reports back. Train 1 at 50 kilometers per hour. All systems normal. Track condition excellent. No vibrations or unusual sounds. Braking is tested. The operator applies moderate braking. The train smoothly decelerates. The braking system is working correctly. Emergency braking is tested. The train comes to a rapid stop without incident. The train stops at a station platform. The operator reports, Train 1 at platform. Distance from platform, 0 centimeters. Stop accuracy within acceptable range. The training wheels are working correctly, guiding the train to the exact position relative to the platform. Doors can be opened without passengers missing the platform by even a centimeter. Testing continues throughout the day. The train operates in various scenarios: acceleration, deceleration, stopping, starting, movement through curves, movement through straightaways. Each scenario is tested multiple times. Data is recorded and analyzed. Additional trains are delivered over subsequent weeks. By the time the metro is scheduled to open, a fleet of trains will have been delivered, tested, and prepared for service. The training of train operators is ongoing, with each operator learning the characteristics of the trains and the operation of the metro system. Beyond the operational systems, the metro requires comprehensive safety systems. These systems protect passengers and staff from various hazards. Fire protection is the most visible safety system. Sprinkler heads are mounted in tunnels and stations. These are connected to water supply systems with tremendous water pressure. If a fire breaks out, the sprinkler system automatically activates, attempting to suppress the fire. But fire protection goes beyond water sprinklers. Foam suppression systems are installed in electrical equipment rooms and other areas where water-based fire suppression would be inappropriate. These systems use specialized fire-suppressing foam that cools the fire and displaces oxygen, extinguishing the flames. Fire detection systems work in conjunction with suppression systems. Smoke detectors and heat detectors are positioned throughout the metro. If smoke or excessive heat is detected, the detection system immediately alerts the control center. Automatic systems begin responding. Fans in the ventilation system can be adjusted to prevent smoke spread. Alarms alert people to evacuate, and emergency services can be dispatched. Emergency exits are positioned throughout the system. From any location in a tunnel, a passenger is within approximately 400 meters of an exit. The exits lead to stairways or vertical shafts that connect to the surface. Emergency lighting provides illumination along exit routes if main power fails. The battery-powered lights automatically activate, guiding people toward exits. The lighting is bright enough for safe navigation without being distractingly bright. Communication systems for emergencies are extensively installed. From any location in the metro, passengers can reach staff by using intercom systems. Train operators have direct communication with the control center. All staff have radio communication equipment. Emergency procedures are established and documented. Staff training includes drills where emergency scenarios are practiced. The response procedures are refined and optimized. Watertight doors are installed at strategic locations. If water seepage becomes excessive in a tunnel section, these doors can be closed to prevent water from spreading to other areas. The doors are sealed and tested regularly. Structural safety is maintained through continuous monitoring. Sensors mounted throughout the tunnel measure ground movement. If settlement exceeds acceptable levels, the sensors alert engineers who can investigate and make adjustments. Track safety is verified continuously. Ultrasonic testing equipment periodically inspects the rails for internal cracks, defects that could lead to track failure. If cracks are detected, the track section is replaced immediately. The safety systems are not activated and then left alone. They're tested regularly. Monthly drills ensure staff are familiar with emergency procedures. Annual inspections verify that equipment is functioning correctly. Continuous monitoring systems operate 24 hours a day, looking for potential problems. The safety systems are so comprehensive and well designed that, statistically, riding a metro system is safer than driving a car on public streets. The level of engineering attention to safety is remarkable. As completion of construction nears, preparation for operation begins. Staff for all positions, station attendants, train operators, maintenance technicians, management, must be trained in their roles. Train operator training is intensive. The training covers the mechanical operation of the trains, understanding of the signaling system, response to emergency situations, and communication protocols. Training scenarios include normal operation and various emergency situations. A training supervisor is positioned in the control center. Train 1, you are cleared to depart from Station Alpha. Signal H1 is green. Accelerate smoothly to 50 km per hour. The trainee operator gently applies power to the train. The electrical propulsion system smoothly accelerates the train. The operator watches the speed indicator, making fine adjustments to achieve the target speed. Speed now 50 km per hour, the operator reports. Acknowledged. Maintain speed toward Station Bravo. Prepare for station arrival in approximately 2 minutes. The trainee operator nods in acknowledgement. As the train approaches Station Bravo, the operator begins moderate deceleration. Train 1 decelerating. Speed reducing to 30 km per hour. The train smoothly slows. The operator monitors the distance to the platform. The train approaches the station at the correct speed. Decelerating further. Speed now 15 km per hour. The platform of Station Bravo comes into view. The operator makes final adjustments, bringing the train to a stop at exactly the right position. The train comes to rest with minimal jerking. The operator has successfully performed the first approach to the station. Train 1 stopped at Station Bravo. Stop accuracy within specification. Doors ready to open. The supervisor nods approvingly. Good approach. Station time, 15 seconds. Doors opening. Simulate passenger boarding. In the training scenario, fictional passengers are boarded in the simulation system. The operator waits the specified station time, typically 30 seconds for passenger boarding and alighting. The operator then prepares for departure. Station doors closing. All passengers aboard. Preparing to depart. The simulation continues with the trainee operator moving the train through the metro network, responding to signals, making stops at multiple stations, and practicing various emergency procedures. The training continues for weeks, with each operator learning until they achieve proficiency. Station staff training is similarly comprehensive. Station attendants must learn the layout of their assigned station, understand passenger flow patterns, respond to emergencies, and maintain equipment. They learn the location of emergency equipment and first aid kits. They learn communication protocols and how to coordinate with other staff. A station manager conducts training with a group of new station attendants. The main passenger flow during morning rush hour will be toward Platform 2. During evening rush hour, the flow will reverse toward Platform 1. You will be positioned to assist passengers and direct traffic flow. The attendants walk through the station learning the layout. They practice their roles repeatedly until they're comfortable. The training continues across all staffing positions. Maintenance technicians learn the metro's mechanical, electrical, and structural systems. They learn troubleshooting procedures for various failures. They learn the maintenance schedule and how to perform required maintenance. Safety training is emphasized throughout all staff training. Staff learn the location of emergency equipment. They learn evacuation procedures. They participate in emergency drills where various scenarios are simulated. The training is thorough and ongoing. A soft opening period is scheduled before the metro opens to the public. During this period, the system operates with staff and invited passengers. The operation is carefully monitored. Any problems are identified and corrected. The staff gain confidence in their roles. During the soft opening, a train operates a scheduled route. Staff monitor every aspect of the operation. Train 1 has departed Station Alpha. Signal status normal. Speed normal. Passenger comfort normal. The train arrives at Station Bravo. Train 1 approaching Station Bravo. Speed reducing appropriately. Station position accuracy normal. The train stops. Train 1 stopped at Station Bravo. Stop accuracy within specification. Passenger satisfaction should be excellent. The soft opening continues for 1 to 2 weeks. Multiple scenarios are tested. Peak passenger loading is simulated. Emergency scenarios are practiced. The system is verified to operate smoothly. As the soft opening concludes, final preparations for public operation are completed. All systems are integrated and verified to operate as an interconnected whole. The maintenance control center is staffed and ready. Technicians monitor sensor data from throughout the system. Any anomalies trigger immediate investigation and response. The systems continuously monitor track condition, electrical systems, structural integrity, and environmental factors. A technician observes data on a monitoring display. Track monitoring system showing all sections normal. No rail stress anomalies. No settlement detected. All bridges and viaducts showing normal sensor readings. Another technician monitors electrical systems. All substations reporting normal voltage. Live rail insulation normal. Train power systems normal. Lighting systems normal. No abnormal current draw. A third technician monitors environmental systems. Tunnel ventilation systems all operating within design parameters. Temperature throughout the system normal. Humidity levels normal. Air quality monitoring systems reporting acceptable conditions. The signaling and control systems are fully operational. The central control computer is monitoring the position of every train. The logic systems are functioning correctly. The backup systems are ready to activate if needed. The communication system is tested. Staff throughout the system can communicate with the control center. Announcements can be made to passengers. Emergency communication is available in all areas. Passenger information systems are activated. The digital displays in stations begin showing scheduled train arrivals. The displays update in real time as trains move through the system. Passengers will be able to see when the next train is expected. The fare collection system is fully operational. The electronic gates at station entrances are activated. Passengers with valid fare cards can pass through the gates. The system tracks passenger movements throughout the system. Security systems are armed. Cameras are actively monitoring all station areas. Alarms are armed and ready to respond to unusual activity. The system is ready to protect passengers and staff. Passenger safety systems are fully functional. The emergency communication system is ready. Emergency lighting would activate if main power fails. Evacuation routes are clearly marked. Staff are positioned and ready to assist if problems occur. The integration testing continues for several days. Scenarios that test every aspect of the system are executed. A train malfunctions. The system responds correctly with control center operators coordinating alternative routing for other trains. A power failure occurs. Backup systems activate automatically. A passenger medical emergency is reported. Control systems immediately respond with emergency services dispatch. Each scenario is handled smoothly. The system is demonstrating the capability to handle complex operational situations. Final preparations include detailed inspections by regulatory authorities. Safety inspectors examine every aspect of the system. They verify that all safety requirements have been met. They observe operational procedures and training. They review documentation and certifications. After thorough inspection, the regulatory authority issues the certificate of readiness. The metro system is approved for public operation. The opening date is set. Opening day arrives. The metro system, which has been the focus of 4 years of construction and months of staff training, is ready to serve its first public passengers. The first train departs Station Alpha at 6 a.m. before the scheduled opening time. This departure is historic, the first revenue passenger service on the new metro system. The train operator is calm and professional. Train 1 departing Station Alpha for the first scheduled service. All systems normal. The control center acknowledges. Train 1, you are cleared for full line operation. Carry the city forward. It's a poetic instruction for an otherwise technical operation, marking the significance of the moment. The train moves through the metro system on its first day of service. The track is smooth. The train operates efficiently. The signaling system guides the train perfectly. The stations are prepared and staffed. Passengers begin arriving at Station Alpha as scheduled opening time approaches. The station attendants welcome the early arrivals. Passengers pass through the fare gates. They proceed to the platforms. The station is clean, well-lit, and inviting. The first train of the scheduled service arrives. Passengers board smoothly. The train departs with a full complement of passengers. Throughout the day, ridership builds. Morning commuters board trains heading toward the city center. The system handles the ridership smoothly. Multiple trains operate simultaneously, each guided by the signaling system to maintain safe separation. A passenger sits on the train watching the tunnel walls pass by. The passenger is experiencing something new: rapid transit through underground passages. The journey that might take 45 minutes by automobile is completed in 20 minutes by metro. Another passenger exits at a station. The passenger has arrived at their destination with minimum hassle. No traffic jams. No search for parking. Just reliable, efficient transit. The control center is abuzz with activity. Operators monitor multiple trains in operation. Train 1 is at Station 7. Train 2 is approaching Station 4. Train 3 is at Station 2. All trains within spacing parameters. Passenger load nominal. The operations proceed smoothly. No emergencies occur. No equipment failures are reported. The system that was constructed through years of meticulous work is functioning exactly as designed. The day proceeds into evening. Passenger loading decreases as rush hour ends. Evening ridership is lighter but steady. The system adjusts automatically. Fewer trains are dispatched as demand decreases. Evening operations conclude. The last passengers exit the system. The final trains are brought back to the maintenance facility. The first day of operation is complete. The control center supervisor makes a final announcement. The metro system has completed successful operation on opening day. 217,000 passengers were transported safely. 38 trains operated without incident. All systems performed within normal parameters. The metro is ready for continued operation. It's a remarkable achievement. 4 years of construction, countless engineering challenges overcome, millions of hours of labor and sophisticated systems integration have resulted in a system that works reliably from day one. As the weeks pass following the opening, the metro system settles into routine operations. Trains operate regularly, carrying passengers throughout the city. The system becomes part of the urban landscape, a quiet background presence that millions of residents depend upon. The daily rhythm establishes itself. Morning rush hour. Trains are full, moving passengers efficiently to their destinations. Midday. Ridership decreases, the system has more capacity. Afternoon. Ridership builds again as people begin returning home. Evening. The rush reverses with people moving away from the city center. Night. Minimal ridership, but service continues throughout the night for shift workers and late travelers. The maintenance system operates continuously in the background. Maintenance technicians conduct routine inspections. Track conditions are examined. Electrical systems are tested. Signaling equipment is verified. Trains are serviced. A maintenance crew enters a section of tunnel at night when no trains are operating. They carry specialized equipment to inspect the track. An ultrasonic testing device is used to examine the rails. The device sends sound waves into the rail and analyzes the return signal. Any internal cracks are detected immediately. No defects detected in this section, a technician reports. Track condition excellent. Moving to next section. The inspection continues methodically along the tunnel. Each section is examined thoroughly. The inspection detects potential problems before they become serious. A crack detected now can be repaired during a scheduled maintenance window, preventing a more serious failure during service. Electrical systems maintenance is similarly routine. A technician checks the connections on the live rail. The connections must be secure and free of corrosion. Live rail connections secure. Insulation normal. No voltage leakage detected. The signaling system is tested periodically. A technician activates a test sequence that exercises every signal in sequence. Signal test sequence beginning. Signals H1 through H127 responding correctly to test commands. Signaling system nominal. Train maintenance is performed on a scheduled basis. A train pulled from service for routine maintenance enters the maintenance facility. Technicians perform comprehensive inspections. Wheels are measured and replaced if worn. Brake systems are serviced. Electrical systems are tested. The train is cleaned thoroughly. The maintenance procedures are documented and tracked. Every action is recorded. If a problem develops later, the maintenance history provides context for diagnosis. Passenger facilities are maintained continuously. Station custodians clean the stations multiple times daily. Any debris or litter is promptly removed. Any graffiti is cleaned immediately. The stations remain inviting and clean. Safety inspections continue. Staff verify that emergency equipment is accessible. Emergency lighting is tested. Fire suppression systems are inspected. The safety systems remain ready for emergency situations. As the weeks become months, operating data accumulates. Engineers analyze the data to identify any trends or patterns. Is any system showing signs of wear or degradation? Are any procedures needing adjustment? The system optimization is continuous. The control center maintains continuous oversight. Operators are alert for any irregularities. Train 7 reporting slight brake pressure variation. Scheduling immediate inspection upon train return to maintenance facility. The system is self-healing in many ways. If minor variations occur, they're detected quickly. The train is brought in for inspection and repair. Service is restored quickly. The true measure of the metro system's success is the passenger experience. The system has transformed urban mobility. A commuter boards the train at a suburban station. The journey that previously required driving through traffic during rush hour now takes a predictable time. The commuter can read, work on a laptop, or simply relax during the journey. The efficiency is remarkable compared to automobile driving. A family uses the metro to travel downtown for entertainment. The parents and children board a train. The children watch the tunnel walls pass by. They experience the efficient movement through the city. The parents appreciate the convenience and safety of public transit. Elderly passengers find the metro accessible. Elevators and ramps at stations allow people with mobility limitations to access the system. Wide doors and handrails make boarding safe. The system is inclusive, serving all segments of the urban population. Students use the metro to travel to schools and universities. The reliable service allows students to plan their schedules with confidence. The cost is low compared to automobile transportation. People with disabilities find the metro particularly valuable. The system provides independence. Passengers who cannot drive can use the metro to travel throughout the city with reliability and dignity. The environmental impact is significant. Hundreds of thousands of automobile journeys have been replaced by metro rides. The reduction in traffic congestion is noticeable. Air quality has improved. Energy consumption has decreased. Economic activity in the city has been stimulated. Areas served by metro stations have experienced increased development. New businesses have opened. Property values have increased in transit-adjacent areas. The metro has contributed to the city's economic vitality. Ridership continues to grow beyond initial projections. The system, initially designed for capacity of approximately 500,000 passengers daily, is approaching that capacity within the first year. Plans for system expansion are already being discussed. The success of the metro system is measured not just in numbers but in the daily experiences of millions of people whose lives have been improved by reliable, efficient transit. The 4 years of construction, the engineering challenges overcome, the meticulous attention to detail, all have culminated in a system that works reliably, safely, and effectively. The metro system's work is far from complete. Even as the first line operates successfully, planning for future expansion is underway. The success of the first line has demonstrated the value of metro transit. The city is planning to expand the system to reach additional areas. Future extensions are being studied. Geological surveys are being conducted. Environmental assessments are being prepared. The planning process is underway, following the same rigorous approach that characterized the first line's development. Technology improvements are being explored. Newer train designs with improved comfort and efficiency are being evaluated. Signaling systems with greater automation are being developed. Energy efficiency improvements are being implemented. The legacy of the metro system extends beyond the physical infrastructure. The engineering knowledge developed through the project has been captured in documentation and learned by the workforce. The expertise in metro construction is now available for future projects. The construction workforce trained through the project brings valuable experience. They understand metro construction methods. They understand the challenges and solutions. This expertise will be valuable for future projects. The metro system has become part of the city's identity. It's a symbol of the city's commitment to modern infrastructure and sustainable transportation. Visitors to the city experience the metro, and many return home expressing admiration for the system. As months turn into years, the metro system continues to operate reliably. Maintenance teams keep the system in excellent condition. The facilities remain clean and inviting. The safety systems remain ready. The system serves its purpose faithfully. The success of the metro system demonstrates the remarkable achievements that are possible through careful planning, skilled engineering, meticulous construction, and dedication to safety and quality. The tunnel boring machines that carve the tunnels are now in other cities, boring tunnels for other metro systems. The expertise of the engineers and workers who built this system spreads to future projects. The metro system will serve the city for 100 years or more. Future generations will use the system, likely unaware of the tremendous effort that created it. But the fruits of that effort, safe, reliable, efficient transit, will benefit millions of people throughout the system's lifetime. As we conclude our journey through the metro system's construction and opening, we reflect on the transformation from an idea into a functioning reality. From the first boring machine beginning to tunnel, through the installation of track and electrical systems, through the commissioning of trains and staff training, through the opening day when the first passengers boarded a train, all of it represents achievement of remarkable complexity and precision. Sleep now, knowing that cities around the world are building similar systems, using many of the techniques and principles we've observed. The tunnels carry passengers silently through the darkness, connecting the city and improving lives. The rhythm of trains arriving and departing, the hum of electrical systems, the careful work of maintenance teams ensuring reliability, these are the sounds of progress and innovation. The metro system stands as a testament to human capability to envision a better future and execute the complex work required to make that vision real.